If I asked you to picture fire safety, I think most people would visualize one thing.
Let me guess, the little red sign.
The little red sign with the white fire extinguisher on it. It's that universal symbol for, here's the absolute bare minimum, just in case.
Right. The last resort.
But what if I told you that effective fire safety is actually a structured, almost forensic science? That it's all about predicting and managing catastrophic risk?
It's so much more than just alarms and red cans.
Exactly. It's about understanding the entire pathway from, the initial tiny spark all the way to the final, really complex environmental fallout.
The whole life cycle of the event.
That's our mission today. We are taking a comprehensive deep dive into the official framework for protecting people and property, pulling from a stack of sources on hazard ID, complex detection, even the tricky business of toxic runoff.
We're really analyzing the whole system built around the threat.
Okay, let's unpack this.
Well, that image of the fire extinguisher, that's where most people's understanding ends. But the science, it actually begins much, much earlier.
With what?
With paperwork, believe it or not. We're talking about the Fire Risk Assessment, or the FRA.
The FRA, right.
An FRA is an organized, really methodical look at a building, at the activities going on inside it, and the statistical likelihood that a fire could start and cause harm.
So its main job is to figure out where and why a fire could start.
Precisely. Where, why, and what kind of harm it would do to people, to the structure itself.
What's fascinating is how systematized this all is. Our sources point to this foundational, standardized 5 steps framework for the FRA.
Yes, and it's mandated across almost all guidance, whether you're talking about a small office or a huge chemical plant.
Or a hospital, even.
That standardization is the key, is how you prevent things from being missed. Critical human factors, environmental conditions, you just can't leave it to chance.
Okay, so what's step 1?
Step 1 is identifying fire hazards. This means looking for the classic fire triangle.
Fuel, heat, and oxygen.
Exactly. The 3 things that have to come together. You're hunting for flammable materials and any potential source of heat faulty wiring, friction from machinery, that kind of thing.
Okay, so you found the things that can burn and the things that can start the fire. What's next?
Then you move to the next critical assessment. Step 2 is identifying people at risk.
And this is where it gets more complex than you'd think.
Absolutely.
Oh.
It's not just the immediate daytime workers. It's the contractors, the visitors, the cleaners who work late at night.
Maintenance staff in weird parts of the building.
Right. And crucially, this step forces you to single out vulnerable groups.
You mean it's not just about counting heads, but about their ability to get out?
That's it, exactly. You have to account for young or inexperienced workers who might not follow the rules, lone workers who won't have help, or people with, say, mobility or sensory impairments.
That someone who can't hear an alarm is a huge risk.
A huge risk. Or someone who can't use the stairs. The FRA forces you to design safety based on the weakest link in that evacuation chain.
Wow. And the sheer range of harms. We're not just talking about burns. The sources mention injuries from panic, stampedes, falling structures.
That puts a huge premium on the next stage. Step 3 is evaluate, remove, reduce, and protect.
So 2 things at once here.
Yes. You're evaluating the risk of a fire breaking out, and you're thinking about the consequences, how fire and smoke might travel and, cut off people's escape routes.
So the reduce part is prevention.
It is. Controlling ignition sources, storing flammables properly, just good housekeeping. The protection part is the active stuff.
The detectors, the signs, the fire extinguishers.
The whole system. You're trying to control the residual risk down to an acceptable level because you can almost never eliminate it completely.
Okay, so if step 3 is about control, the last 2 must be about keeping the system sharp.
Correct. Step 4 is record, plan, inform, instruct, and train.
You have to write it all down.
Everything. The hazards you found, what you did about them, the risk level. And you need detailed emergency plans. Critically, you have to practice evacuation drills regularly.
Because if you don't practice, the plan is just a piece of paper.
It's useless. And finally, step 5 is review. The FRA is a living document, not something you file away.
So you look at it again after an incident, or if the building changes.
Exactly. Or just periodically. It has to stay current.
That whole structured approach is what makes it a science. But given that risk of injury, panic, crushing, it puts a huge premium on knowing the instant a threat starts. How do buildings, listen for fire?
That's where you get into the science of detection. It's all based on identifying the physical changes that combustion causes.
What are we looking for?
Essentially 4 distinct signatures: invisible products of combustion, visible smoke, radiant energy, which is just the flame itself, or a simple temperature rise.
It sounds like you need specialized ears for different environments.
You do. The physics are the same, but the tech is so much better now. Take smoke detectors. There are two main types.
Okay.
You have ionization smoke detectors, which are incredibly sensitive to small smoke particles,
Yeah.
the kind you get from a clean, fast-burning fire.
So perfect for a server room or somewhere clean.
Ideal. They react really fast to minimal smoke. But then you have optical detectors. They're designed to see the larger smoke particles from a slow, smoldering fire. Think of, like, a sofa cushion.
So you have to pick the right one for what's most likely to burn?
You have to.
Yeah.
If you choose wrong, it won't be effective.
And if smoke is just too, I don't know, sensitive for the environment, like a dusty workshop, you look for heat.
Exactly. Heat detectors are crucial. You have fixed temperature ones that trip at, say, 57 degrees Celsius. But they suffer from something called thermal lag.
A delay.
A delay. It takes time for the air to heat the sensor up. The more sophisticated type is the rate of rise detector.
So it looks for a sudden spike in
A
temperature.
rapid increase, yes. Not just a fixed number. This is so important because it compensates for slow, normal changes. A room getting warm from the sun won't set it off, but a flash fire will, instantly.
And for huge open spaces.
For that, you have radiation detectors. They actually see the infrared or UV light from a flame. They're incredibly fast. You use them in aircraft hangars, places like that.
But they have to have a clear view.
A clear line of sight. If something gets in the way, even just some clutter piled up, the detector is effectively blind.
It's amazing how sophisticated that is compared to the purely manual systems, like a handbell or a whistle.
Which might still be okay in a tiny, low-risk workplace. But they rely completely on one person noticing the fire and then acting correctly.
The liability there is huge. One person panicking and the whole system fails.
And the challenge for any system, manual or automatic, is false alarms. If it goes off all the time for no reason, people stop believing it.
They just ignore it, and that delay can cost lives.
And we find it often comes from simple mistakes in the FRA. A high-sensitivity smoke detector in a kitchen is just asking for trouble. Or malicious activations, someone breaking the glass for fun.
So in a really critical environment like a data center, how do you build in more reliability?
You add layers of confirmation. They're called voting systems.
Voting systems.
Instead of one detector triggering the alarm, the system might need 2 out of 3 detectors in a zone to agree that there's a fire. It dramatically cuts down the chance of a false alarm from one faulty sensor.
That makes sense, because once it's confirmed, you're shifting from detection to, well, to active intervention.
To suppression.
Let's start with the big fixed systems that are built into the building's infrastructure.
Right. So the one everyone knows is sprinklers. The crucial thing here is that the heads are sealed. Only the ones right near the fire actually rupture.
Which limits the water damage.
Exactly. It's a targeted approach. Then you have drenchers. They're usually on the outside of a building.
What do?
They create a continuous water curtain to shield a structure from the heat of a fire next door, protecting it from radiated heat.
Okay, and for high-risk enclosed spaces.
You might use a total flood system. This dumps something like CO2 or an inert gas into the room to displace all the oxygen.
Which suffocates the fire.
But it's also highly dangerous to people.
Oh.
So they had to have manual lock-offs and clear warning systems.
And for the absolute highest risk scenarios.
That would be a deluge system. Here, all the heads are open. When it goes, a valve opens and water floods the entire area at once. You see this in places that store explosives or highly flammable liquids.
All these fixed systems rely on knowing your enemy, the fuel. And that brings us to fire classification, right? The chemical Rosetta Stone of firefighting.
The perfect way to put it tells you exactly what tool to use.
So you have the classes. Class A is your standard organic solids.
Wood, paper, textiles.
Class B is flammable liquids like petrol or paint. Class C is gases like propane. Class D is for combustible metals.
Very specialized. Sodium, magnesium, things that burn incredibly hot. And then there's Class F.
For commercial cooking fats and oils.
Yes, that's a crucial modern one. And this all ties back perfectly to the 3 ways you can actually put out a fire.
Breaking the fire triangle.
Exactly. Starvation is removing the fuel. Simple as turning off a gas valve.
Smothering is removing the oxygen.
Right, with a fire blanket or foam. And finally, cooling is removing the heat, which is what water does so well. It absorbs huge amounts of heat energy.
And the steam it creates also helps smother the fire.
It does both.
So if the classification is your guide, grabbing the wrong portable extinguisher could be, well, worse than useless.
It could be incredibly dangerous. Using water on a burning pan of oil, for example, will cause a massive conflagration. It just spreads the burning oil everywhere.
Which is why they're color-coded.
Yes, a red body with a colored band. So water is just red for Class A solids. Foam has a cream band, good for A and B fires.
And the blue one.
That's dry powder, your multi-purpose ABC powder. Good for solids, liquids, gases, and electrical fires.
Okay. And CO2 is black?
Carbon dioxide, black band. Excellent for liquids and electrical fires because it smothers them. But you never, ever use it on a hot Class D metal fire.
Why not?
The extreme temperature can cause a dangerous chemical reaction with the CO2.
And finally, for those Class F cooking fires.
You need wet chemical, which has a yellow band. It works through a process called saponification.
Fancy word for?
It basically turns the hot fat into a non-flammable soap. It creates a foam that seals the surface and stops it from reigniting.
And just having these isn't enough. The positioning and maintenance is just as regulated.
Oh, absolutely. They have to be conspicuous on escape routes and no more than 30 meters apart. And the maintenance is a 3-tier system.
Monthly visual checks and annual service.
And then an extended service every 5 or 10 years.
But training ties it all together. People have to know what to do.
They have to. They need to know which type to use and, more importantly, to understand that it's only for first aid treatment. Evacuation is always the priority.
What's the general rule of thumb?
If you're trained and you use 2 extinguishers and the fire isn't out, you leave immediately. Close the doors behind you to contain it.
We've covered preventing, detecting, and suppressing the fire to protect people and property. But we have to talk about the final, often overlooked risk,
The environmental damage.
the aftermath.
This is a huge and growing area of fire safety science because the act of fighting a large industrial fire, well, it creates its own massive environmental hazard.
How so?
All that water runoff. It carries chemicals from whatever burned the inventory, the building materials, even from the foam itself. And this toxic soup can get into the groundwater or just pour into rivers.
So you're trading an immediate crisis for a slow, toxic, ecological disaster. Can you give us a sense of the scale of this threat?
The textbook example is the 1986 Sandoz chemical fire near Basel in Switzerland.
What happened?
A huge warehouse full of agrochemicals caught fire. The firefighters did their job, but the runoff water, we're talking hundreds of thousands of liters, swept thousands of liters of toxic pesticides and deadly mercury straight into the Rhine River.
Oh, my God.
The result was catastrophic. It created what they called the Rhine red tide. It essentially sterilized the river. It killed nearly all aquatic life, fish, eels, everything, for 180 kilometers downstream.
180 kilometers?
It was a profound lesson in the long-distance impact of contaminated firewater. It basically rewrote the rules on industrial containment in Europe.
And these chemicals don't just disappear. Our sources mention things like PFOS, a chemical in some old foams.
A forever chemical.
Yeah.
It's bioaccumulative, toxic, and it stays in the human body for a very long time. Ground contamination from these can pollute water sources for decades.
So pre-planning for containment is essential now.
Absolutely essential.
Yeah.
You have to know what chemicals you have and how sensitive the local environment is before a fire even starts. The methods fall into 2 categories.
Permanent and emergency.
Exactly. Permanent systems are things you build in advance. Impermeable lagoons, purpose-built tanks, or shut-off valves in the drainage system to isolate the site.
And emergency measures.
That's when you're creating temporary bunding. Building barriers with sandbags on a car park to hold the water, or you designate sacrificial areas to collect the runoff.
And once it's all collected, you have to dispose of it as hazardous waste. It turns fire safety into a massive chemical waste management problem.
It does.
So what does this all mean? We started this deep dive with that simple, familiar red fire extinguisher, and we've ended up tracing this incredibly complex, structured, scientific process.
It shows that effective fire safety isn't reactive at all.
It's proactive. It requires you to master risk assessment, understand how different detectors listen for different signatures, and know the specific chemistry of the fire you're fighting.
And it means true safety is about anticipating every single threat, from the immediate danger to life inside the building,
Governed by escape planning.
to the long-term complex chemical threat to the world outside, which requires containment planning on an industrial disaster scale.
It's a huge undertaking.
It is. So think about this as you consider a complex, modern, high-risk industrial facility. You have thousands of volatile chemicals. The fire triangle needs heat, fuel, and oxygen. Given the sheer variety of materials, the difficulty of detection, and all the containment requirements we just discussed, which of those 3 foundational elements heat, fuel, or oxygen, is the most difficult to truly control or eliminate in that kind of large-scale environment. And why?